So the theorem, this one's a theorem, it's supposed to postulate. Phonon expansion can occur when two nuclei fuse in a lattice. I looked up in the dictionary earlier today. Theorem is a statement which can be proven from known accepted theory facts. And in this case, this has the ranking of a theorem. I'm not sure anyone would disagree. Well, this was the place where I started in 1989. I said, suppose you have a quantum mechanical two-level system. You have a complex physical system. You're doing quantum model, and I replaced the complex quantum system with a simpler idealized system. So here's my simpler idealized system. There's an upper state which represents molecular D2 within the metal Deuteride. There's a ground state which represents helium-4. And there's an oscillator which represents the phonon modes in the lattice. The question is if you hook up a two-level system to an oscillator, what happens? Well, this is a problem that's been long studied in the physics literature. Basically, the picture of it is you have an oscillator, and I've added some broadening since phonons are lossy and oscillators wind down, so there's a line width associated with it. The two-level system may not be centered at the same frequency the oscillator. There might be some mismatch. The phonons, for example, might be around 50 millivolts. The two-level nuclear system might be at 24 megavolts, so there's a little bit of a difference between them. The width, of course, of a phonon line is nowhere close to 24 megavolts on the second. However, the two-level system overlapping with the oscillator, the lines overlap, and then you can transfer energy as a first-order process. Now, I modeled it, and I very early on, in fact, in April of 1989, I proposed models of this sort to try to begin to understand how the coupling might work. And basically, what I found is that it doesn't work very well. The interaction's too weak from the molecular state. The off-resonance is bad. Even if you have a very nonlinear interaction, there's just no way to get the energy in, so it's broken. I said, well, in those days and in these days, I said, well, suppose you have many sites interacting, two-level systems of many sites interacting with the phonon field, the coupling might be stronger. Maybe that helps. And in 1989 and again 1998, I came back to this problem, and the answer is coupling's very weak, and it just doesn't go. You've got this big quanta, the lattice one's small quanta. You've got $1 and your bubblegum machine takes pennies. Oh dear, I don't pennies anymore. But you try to shove your $1 into the bubblegum machine that wants pennies and it doesn't go. You try to shove the large quanta into an oscillator that takes a small quanta, it just simply doesn't want to go. You got to chop up your dollar bill into pennies before you can make it work. So the only way around this at this level is the following argument. Suppose your phonon mode is here and it has some line width. Suppose your two-level system is out here, 24 MeV, 50 millivolts, large distance between them. The question is what's the line width look like out at 24 MeV? Okay, it sounds like a weird question. You go to the literature and you flip through the books and you say, well, what's the response of the phonon mode at 24 MeV? Scratch your head and say, well, what a dumb question to ask. No, it's not been considered. Nobody's had any reason to consider what the response of a phonon mode would be at high frequency. Now, you can make some progress by thinking a little bit about the problem. Coupling between phonons and other phonons can give width to a phonon wire shape.
Yeah, if I can just interrupt, when you say that no one has dealt with that issue, actually, local phonons, very highly localized phonons, been identified at that frequency, and we're very close to it, in palladium deuteride and palladium hydride in the context of the fact that that material becomes a relatively high temperature superconductor at
Okay.
So in other words, those
Do you
modes
think-
have been, those phonons have been identified.
Certainly localized phonons have been identified, and I don't need to indicate that the superconductivity and the work that you've done is not important.
No, I'm just stating an experimental fact that in the literature, not my literature.
No,
but,
there's neutron scattering that's identified and observed. When neutrons bang against the deuterons, you can see both the center frequency, you can see the line shape as well. So where there's large response, you can see it in the neutron spectrum directly. You might expect that the phonons could generate some line shape and response due to coupling of electrons. However, that's at the electron volt level, so you still got to get out to 24 MeV. So let me put a question mark here to be followed up shortly. Suppose the phonons happen to couple with nuclei, namely if your phonon node actually were coupled with the nuclear system, then if you drove the phonon node at a frequency which the nuclear system would respond, it could be thought of in terms of equivalent line shape. This initial thought was something I was using back around 1990 or so, and it's going to come up again shortly. Conjecture. Coupling between fusion reactions lattice possible in the framework of discussion so far. If lattice nuclear coupling can give a admittedly small contribution to a phonon line shape in the MEV region. Okay, new physical mechanism. Basically, up to this point, the notion of two-level systems and oscillators, basically we largely ran out of steam. We're not going to get, from the analysis we've talked about so far, we're not going to get a lot of reaction, not going to be able to convert the power decently, and so forth. Now, the reason for it is that the coupling is weak, the quantum is big, and the oscillator quantum is small, and so forth. So at some point, you've got to turn back to experiment. You scratch it and say, okay, experimentals show me something that will help me sort out mechanism. And the claim is that DD fusion by itself in the lattice Jones's observations, while it's nice, it doesn't tell you anything about mechanism. The Pons-Fleischmann claim of heat with no energetic reaction products excludes a lot of things, but it doesn't tell you anything positive. There's no positive statement in that about what's happening. So what I'm hoping for is to find an experiment that will tell me something positive, that I can make a positive theoretical conjecture out of. There's an experiment that was reported by George Chambers, which at the time was the only observation of it, and the signal wasn't very strong and so forth. But George Chambers worked with a ECR source, electron cyclotron resonance deuteron beam, which had deuterons come in, deuteron ions, I believe, come into floating deuteride coil. Graham, correct me if I'm wrong, it's around 500 eV or so. Out of this was detected alphas at 18 to 21 MeV. Now, alphas at 18 to 21 MeV is a very energetic alpha. If you have alpha decay of radioactive nuclei, about the highest energies you get is about 5 or 6 MeV. And the more energy that you get, the faster the alpha tunnels through the barriers. So things with energetic alpha emission have very fast decay. The observation of energetic alphas here are very unusual, very difficult to account for by any reaction mechanism. It's not a normal part of nuclear physics. If a deuteron comes in, even with a fast beam and hits something, you're unlikely to generate alphas at 21 MeV through normal two-body interactions. After thinking about this for a long time, the conjecture arose that you started out with two deuterons and you made helium-4. Two deuterons come together and makes helium-4 at one site. At another site, if you have phonon exchange, the phonon node might talk to your two deuterons and it might talk to a plating nucleus.